Yeah,
Yeah, okay, fine. So good morning, everyone. Those who are joined from this platform and also joined from the YouTube. So today I'll be talking about extrasolar planet and Earth-like planet. These are very fascinating objects. Actually, from past 2 decades, more and more scientists are interested in discovering those strange worlds. So before I go into detail, I'll just give a very brief definition of what are extrasolar planets. So extrasolar planets are the planets which orbit stars other than our sun. So they are not orbiting our sun, but they are orbiting stars other than our sun, and we call them extrasolar planet. And they are very fascinating objects because they show how diverse the other planetary system can be, whether there might be life on the planet, which we have discovered around other stars. So yeah, so this is what I'm going to talk about. So before I go further detail into my talk, let's go back a little bit into the history of the discovery of the planets. Actually, it was the ancient Greeks who discovered the first 5 planets: Mercury, Venus, Mars, Jupiter, and Saturn. And what happened that they have also counted Earth, Moon, and Sun as a planet, along with these 5 planets. Until then, Earth was not considered as a planet, but rather it was thought as a celestial object around which all these bodies is revolving. And that was the case until 16th century, when the Nicolaus Copernicus placed the first acceptable planetary model, which tells that Sun was placed at the center of the universe, and Earth and all this planet is orbiting the Sun. So that was the case until 16th century. And then in early 17th century, by the invention of the telescopes, led us the discovery of the farther planet like Uranus and Neptune, which were then added as a solar system planets. And Pluto was considered as a planet until 2006, and then it was discovered as a planet. So this was the case until 1995. So until 1995, we were just knowing that there were only 8 planets in our solar system, and we were not aware about is there any planetary systems or is there a planet around other stars. And then in 1995, the discovery of the first extrasolar planet around a sun-like star. So name of that the star was 51 Pegasi. So here 51 Pegasi is the name of the star, and B is the planet. So if you have multiple planetary system, you have B, C, D, E in a small alphabet. So the first exoplanet was discovered in 1995 around a sun-type star, and then the plethora of the box opened, and then lots and lots of discoveries happened. Until today, we have discovered around more than 5,300 exoplanets. So till today, we know that there are more than 5,300 exoplanets out there apart from our solar system. So let's define what are planets first. I think everybody know the definition of planet because they might have learned in their elementary school. So according to the IAU definition, you can call an object as a planet if it's orbit a star. So the object must orbit the star. The object should have enough mass and the gravity so that force that object into spherical shape. So the object has to be in a spherical shape. And the third important criteria to call any object as a planet, that it should clear its orbit. There should be nothing. Nothing should come in the orbit of that object. So these are the major criteria an object has to satisfy to define them as or to call them as a planet. Okay, fine. So why looking for exoplanets is important? Why we want to look for exoplanets? So these are some questions which scientists here in PRL and all over the world are trying to answer. So I'll just draw your attention in this in our solar system, in our solar systems. So in our solar system, we see three basic patterns. I think everybody is aware of these three patterns. First pattern is that the planets in our solar system has nearly circular orbit. And it's a very interesting fact that there is no law of physics which says that orbit of this planet has to be circular. Actually, in general, orbits are ellipses, and it ranges from perfect circular to very elongated orbits. So it seems that some spatial process might have happened in our solar systems, which makes the orbit of our solar system planet nearly circular. Great, that's fine. Let's go on the second pattern. So the second pattern which we see in our solar system is that the orbits of the planets are nearly well aligned with each other, and also with the rotation of the sun. So this is again very strange pattern we see, very unique pattern. And the most important third pattern is related to the size and the composition of the solar system planets. So what we see in our solar system, that the rocky planets are lying in the interior like Mercury, Venus, Mars, and the Earth, whereas all the gas giants are the exterior. Again, it seems that all are sorted in a way that it seems quite a coincidence. So is our solar system is unique in the universe? We don't know that. And the other questions is that what fraction of stars are having planets which are orbiting them? And how many of them are an Earth-like planet which can host life? And what about the idea of our solar system formation, like these three pattern? Do we see other patterns in those systems? So these are the kind of questions which we try to answer by looking at exoplanets. Just to give you a visualization how diverse a planetary system can be. So this you see the sun is sitting here. This is a scaled version of solar system. So the sun is sitting here, and these are the terrestrial planets, orbit of terrestrial planets. This is Saturn and Jupiter, and you can see all those systems are discovered till now with their orbits. You can form more and more many planetary systems in a very close orbit to their parent star. So this is this is a kind of a visualization to show you or to compare the orbit of different planetary system compared to our solar system planets. Okay, so what types of exoplanets do we see? So usually we classify exoplanets into 4 broad categories. The first one, so on x-axis you are having the period, on y-axis it's a mass, in the Jupiter mass. So the first type of planet, the first classification of exoplanets we call hot Jupiter. They are lying here. These are massive giant objects similar to our Jupiter in our solar system in the size, but they orbit very close to their parent star. You see here on the x-axis that the period is around 10 days. You see our Jupiter takes 12 years to complete one rotation around the sun, whereas these giants, hot Jupiters, are just revolving around their star in 10 days, some are even less than 1 day or 2 days. So due to their close proximity to their parent star, they experience a very high temperature, and that's why we call them hot Jupiters. And their close orbit and large sizes made them some of the earliest exoplanets to be detected. The second class of exoplanets we call mini Neptunes. I have not labeled it here, but they are lying somewhere here. So mini Neptunes are the rocky planets, but they are bigger than our Earth. They have hydrogen and helium in the atmosphere, but they are more or less similar to our ice giants like Neptune in our solar system. They are often found further away from their parent star. You can see here, and they are not as hot as compared to the hot Jupiters. The third class of exoplanets are we call super Earth. So super Earth, you can see they are lying here. They are rocky planets that have mass larger than the Neptune and the Uranus, and they comes in vast various sizes, and they could be rocky. They could have a rocky surface, thick atmosphere, or even a combination of both. And now from past 5 years, these super Earth are one of the most common types of exoplanet discovered so far. So in initial days, Earth Jupiters were so common, but then due to the advancement of the observational technologies and the detection technology, now we are seeing super Earths more and more in numbers. And the last type, the kind of exoplanets is called terrestrial exoplanets. So these are the exoplanets which orbits their host star at a distance, so that they can have liquid water on their surface, and they can harbor life on their surface. So these are the 4 different types of exoplanets: so hot Jupiters, mini Neptune, super Earth, and terrestrial. So these are the diverse nature of exoplanets. So in terms of mass, you can see here on x-axis the semi-major axis, on the y-axis is the planetary mass, and you can see how diverse they are. Yeah, you can find them in different mass range. And when you zoom in these objects, our Earth and Mars is lying here, and you can still see a Jupiter kind of exoplanets orbiting very, very close to their parent star, and they comes in a vast mass ranges. The eccentricity of exoplanet describes how elongated or circular their path can be around their host star. So some of the exoplanets are having very high eccentric orbits, whereas where others could have similar circular orbits similar to our solar system planets. So this is the diverse nature of exoplanet in terms of eccentricity. In terms of inclination, it's again they are so diverse in nature. So exoplanets can have a wide range of orbital inclination, from nearly perfectly circular to perfectly aligned orbits. And all those information will help you to understand the various dynamical processes or other chemical processes happening during their formation. So the reason I showed you these plots is to just give you an idea how diverse these exoplanets could be compared to our solar system planets. Okay, now let's talk about their detection. So on the x-axis, you are having the discovery of year, and on y-axis the number of detection. So the first exoplanet was discovered in 1992, but around a dead star. We call it pulsar. So the first exoplanet was discovered around pulsar. So we are not. So usually they would debate that whether we should consider it as a planet or not. But then in 1995, as I told you before, the first exoplanet was discovered around main sequence star, and over the years, the number of exoplanets detected per year increases, and thanks to the advancement of various detection techniques. And here you can see the majority of the exoplanets which have been detected is using this green color, is because from the transit method. So I'll be talking about these methods in my upcoming slides. So the transit method has been responsible for most of the significant portion of the exoplanet discoveries. There are other detection techniques which is also contributed in their detection, called radial velocity, direct imaging, and microlensing. So let's see how we can detect those planets with those techniques. Okay, so let's first talk about detecting them directly see them. So this direct detection techniques involves the detection of exoplanet which is just sitting next to the star. Actually, this technique is a very strange way of measuring the power which is emitting by the planet. Actually, it is very difficult to measure the power because, as you all know, that planets are very faint objects. They don't emit much. Also, they are sitting very close to their parent star, which is much times brighter than the planet. So how can we detect them directly? What are the techniques? So the one way to do is that we can directly image the young planets. Why? Because young planets, when they form, they are much hotter, so they emit more radiation, which means they are brighter and easier to detect, easier to directly detect. Another way we can improve the chances of a detection directly is to going to see them in the infrared part of the spectrum, because planets are 1 billion times less luminous than the star in the optical when you go in the infrared. So the contrast ratio between the planet and the star is small in infrared as compared to the optical. So if you want to see them directly, you have to observe them in the infrared wavelength. And the third way we can see them directly is to find a planet which is not that close to their star, but rather very far away there from parent star. So these are three ways we can perform the direct detection of planets. And this method, which you call direct detection technique or direct imaging, so this method is called direct imaging, and this is just starting now recently, and it is still in a developing stage. Just to give you an analogy how this direct detection technique works, so what you see on your screen is a very bright, high-power night lamp or street lamp. You can see how bright it is. And let's assume you have a very small power bulb sitting next to this lamp. Now you probably hardly be able to see this the bulb which is having less power because it is illuminated by this street lamp. So how can we, or what are the way we can see at least some sort of radiation or power coming from this lamp? So the one way is to block the light using some sort of obstacle. So if you put obstacle on this this bright power lamp, you might be able to see the radiation coming from this less powered bulb. So this is how the reason I show you this this slide or this image is to give you an analogy how the direct imaging technique works. So let's see the detection of planet using direct imaging techniques. So what you see here is a multi-planetary system, 1, 2, 3, and 4. So these are all the massive planets, and the movie which you are seeing here, it's made by making the observation of around more than 10 years. It's just not only one observation, but it's a multiple observation from past 10 years because they are orbiting very far away from the parent star. So how this technique works is that at the center of this image, you see the star is sitting here. So somehow you block the star of, somehow you block the light of this star. And the way we do, the way that the technician do is using the coronagraph. So with the use of coronagraph, you block the light from the host star, which is sitting at the center. And what you see is the thermal emission from the planet, which you can detect. So in this technique, the brightness ratio between the planet and the host star depends on the planet size. The distance between the planets and the planetary star, and also the characteristic of the planetary atmosphere. So in this image, so the name of this, so this is the first discovery of 4 giant planets around the star we called HR 8798 in 2008. All those 4 stars are very massive planets. They are 10 times bigger than our Jupiter. They are 10 times further away from the host star. And as I said before, this method is effective in detecting the young and massive planets, which are located very far away from the host star. So this method is somehow biased towards a specific population of exoplanets, and we potentially miss smaller planets which are orbiting very close to their host star. So till now, around 12 to 13 planets have been discovered using these techniques. This technique. Yeah. So what are the other way? What are the other indirect method we can detect the planets? So there are many actually, but in this today's talk, I'll be just covering 3: real velocity, transit, and microlensing. So let's talk about the first indirect way of detection of planet, which we call a radial velocity method or a Doppler method. So the fundamental principle behind this method lies in the fact that a star and a planet which is orbit, the star and the planet, they exert gravitational force on each other because they have mass, and as a result, they both orbit around their common center of mass, which is here, this one, this inner circle. So when a planet orbits a star, it causes a star to wobble around because of the gravitational pull. So this wobbling of the motion by the star, because we cannot see the radiation from the planet, what we see is the light coming from the star. And since these are two body system, they have a gravity, they rotate, they orbit around common center of mass. So what happened that because of the gravitational pull, the stars also wobble and induces a periodic shift in the star spectral line. So which we can observe in the spectrum. So what you can see here, when the star is approaching towards you, you see the spectral line is, the star is going away from you, the spectral line is red shifted, and when it is coming towards you, the spectra is blue shifted, the spectral line is blue shifted. And if there is a planet, then you see this shift has a periodicity. Yes, this shift are periodic in nature. So by measuring this periodic shift in the star spectrum, one can infer the presence of exoplanets. So in this video, what you can see here, so this is a star, this is a planet, and let's say we are sitting here on the Earth and we are observing the star. And this cross here is the center of mass. So the star is rotating, and star and planet is rotating around the center of mass. And what you see when the star is coming towards you, you see the lines are blue shifted, and when it starts going away from you, you see the star is red shifted. And if there's a periodicity, we see such curve. We call such curve the radial velocity curve. So the amplitude of these peaks we call the semi-major amplitude, and the difference between these two peaks we define as the period. And this is a very important method because using from this method we can get the mass of the object which is orbiting the star. So in the case of Earth, the shift in the radial velocity is 10 centimeter per second, which is very, very small. Whereas in case of Jupiter, it is around 12.5 meter per second. So let's see how let's see how this Doppler curve or radial velocity curves look like for the exoplanets. So the first exoplanet in 1925, which was discovered by these two scientists, and because of that discovery, they got the Nobel Prize. It looked like this. So on the x-axis, you have the time. On the y-axis, you have the velocity. So what you see here, when you see the star is approaching towards you, you see the velocity is negative. It is a blue shifted. And when the star is going away from you, the spectral lines are redshifted, and you see the increase in the velocity. And you see this sinusoidal behavior because the star and the planet which is orbiting the star has some period. So this periodic variation which you see will tell you the information that yes, there is a planet which is orbiting that star. So the first planet, which was discovered by these two scientists, has a period of 4.2 days. You can see orbiting very close to the star. The semi-major amplitude is around 56 meters per second, which means that it's quite big in size, even bigger than our Jupiter. And the eccentricity is 0.01, not circular, nearly circular orbit. So that was the discovery around planet around Sun-type star. But the interesting fact is that the second nearest star to our Earth, also, which we call Proxima Centauri, also hosts planets actually. So what you see here is the radial velocity curve. So all these red dots are actually the observation, and you see this periodic behavior when the star is approaching towards you and going away from you, approaching towards you, going away from you. And you see this periodic behavior, and from this and from various further analysis, we were able to say that that's the second nearest star to Earth, which called Proxima Centauri, has a planet. So, and then the mass of the planet is 1.3 times the Earth. So this discovery got a lot of attention in the media. Okay, fine. Now let's talk about some strange radial velocity curve. So what you see here, the radial velocity curve of Kepler 1704b. So Kepler is the telescope which discovered this, which observed this star and discovered this planet. And here you can see this radial velocity curve does not look like a wavy pattern. Sorry. Like this, which I showed you here. It has some sort of strange pattern. So what is happening here actually? We don't understand. So the scientists try to understand, and what they found that when a star is approaching towards us, by some reason it shoots away from us. Like away from us means when we are observing them. So what is going on here? And then scientists found that the orbit of the planet, which is orbiting this star, is not circular but elongated orbit, elliptical orbit, highly eccentric orbit. So what you see in this plot figure, this blue dot is the star, Kepler 1704b, and these different circles are the orbit of the solar system planets, and this solid black curve is the orbit of the planet, which is revolving around Kepler 1704b, and you can see the very highly eccentric orbit. So these are the kind of surprises you get when there are exoplanets out there in the universe, and they are quite completely different than what you see in our solar systems. So that breaks the pattern we see in the solar system, the three pattern which I talked about in my first or second slides. So as I talked before, the solar system planets have a nearly circular orbit, but in this case it's very elliptical orbit. So that breaks the pattern of a solar system, and also contradict the theory of planet formation. Because till now, whatever theory of planet formation has been developed is to explain the solar system planets. But how can you explain from those theories these strange systems? So yeah, these are the kind of surprises you see when you try to observe or study exoplanets. Okay, fine. So what sort of information we can gather from the radial velocity technique? So first is the planet mass. So the shape and amplitude of the radial velocity curve will tell us about the mass of the exoplanet. So as I said before, a more massive planet will induce a large wobble on the host star, which led to a higher amplitude in the radial velocity curve. Whereas for smaller planet, the amplitude is very small. Also, you can get information about the orbital period. So if a planet has a small period, you can see these cycles quite frequently. Whereas if a planet has a longer period, you don't see that frequent periodicity so frequently. It also tells about the shape of the orbit. So if you have a circular orbit, then you see purely well sinusoidal shape. But if you have a eccentric orbit, you see such shape. So these are the these are kind of information you get and you obtain when you do when you detect planet using the radial velocity method. Now let's talk about the second method. So this method is called the transit method, and it is very important method because the majority of the exoplanet which has been discovered till now is based on this technique. Again, this technique is an indirect method, and we don't see the planet directly like we have we were able to see in the direct imaging technique. So in this technique, again in transit method, we don't see the planet directly, but we see the effect of planet on the star. So how this technique works? Okay, let's see. So this method works only for star-planet system which has orbit aligned in this way. The orbit has to be aligned in this way. We call it edge on orbit. If you have face on orbit, this method does not work. So what happened in this method is that when the planet is between this is the planet, this is star, and let's say you are sitting here, and when the planet is between the Earth and the host star, the planet will pass through in front of the star. So and what it does, it blocks some amount of light. So you see dip in the star light or star brightness. So when it is not passing, then this planet is not passing between the Earth and this and in front of the star, you see a straight, no change in the brightness. But once this planet, see, is coming between us and the star, and it blocks the light, you see dip in the star brightness. And because star is blocking, this planet is blocking the light which is coming from the star. And this duration of this transit, we call this when this planet passes in front of the star, we call it the transit. So the duration of this transit and the depth of this transit depends on how big the transiting planet is. And by monitoring these periodic changes in the brightness, one can again tell the presence of exoplanets and gather information about the size, orbit, and other characteristics. So basically from this technique, we can get the radius ratio of the planet star system. Okay. Let me show you the example of some transit data compared to the real velocity data. So what you see here is the transit data, not the real velocity data. So this is a transit curve of head P7b planet. So when the planet is not passing between in front of the star, you see no changes in the star's brightness. You see no changes. But once this planet is passing in front of the star, it blocks some of the light of the star, and you see dip in the brightness of the starlight. And once it goes away, again you see no changes in the brightness of the star. So this is how this is for the transit light curve. So what you see here on the y-axis is the relative brightness, and the decrease in the brightness is around 9%. So the planet is blocking 9% of the starlight. So this is how the transit light curve of a planet look like. And so using these techniques, people have discovered the planets. So this planet, which is discovered using this technique, having a mass of 1.792. By the way, the mass was derived using the radial velocity technique. So again, for the mass, to derive the mass of the planet, you need to do the radial velocity observation. Whereas in order to get the radius of the planet, you can use the transit method. So from the transit method, the scientists had derived the mass of this planet around 1.36 times the Jupiter radius. So it's quite big than our Jupiter. And the orbital period is 2.2 days. You see, our Jupiter is revolving around Sun in 12 years, whereas this hot Jupiter is orbiting this star in 2.2 days. So it's very close orbit. See, the distance between this planet and its host star is 0.03 AU. So is it possible, can we fit this hot Jupiter in this solar system plot? The answer is no. We have to zoom in, and when you zoom in, then only you can fit the orbit of this planet. And you can see this HET-P 7b planet is orbiting very, very close to its parent star. It's orbiting in very tight orbit compared to Mercury orbiting our Sun. So these are some interesting facts. Again, you observe and you see when you study exoplanets. Okay, so what I showed you was just one planet orbiting the star. What about if you have a multi-planetary system? Then how the transit curve look like? So what you see here, the transit curve of multi-planetary system. So here we have three different kind of planets revolving around this star. One can see here that the period of this deepest transit is not that frequent compared to these small transits. You can see the first transit deepest transit is happening here, and the second one is happening after, let's say, around 70 days. Which means that this planet, which is showing the deepest transit, is orbiting far away from its parent star. Whereas these small transits are so frequent. This small transit happening in 15 days. You can count here. In 15 days, you are able to see this transit, which means that the planets are orbiting very, very close to its parent star. So this is how the transit curves of multiplanetary system look like. You have different periods, you can see different depth, and also their duration is different. Just to give you visualization, how the transit curve of multiplanetary system look like. So this is star. This one planet is going in front of star, and you see decreasing the brightness of the starlight. And when it goes away, you again the star, you see no change in variation. And when this planet comes, you see deep, and this planet also blocking. So you see further deeper transit in the light curve, or we call it transit curve. So yeah, so this is just to show you the visualization. How the transit curve or different types of planets look like. So if you are trying to find a Jupiter-sized planet, then you see much deeper transit. So around, you see much deeper transit. Whereas if you are looking for an Earth-like planet, the transit depth is very, very small. You can see 0.01%. The Earth-like planet is just blocking 0.01% starlight, and it's very, very difficult to detect such a small decrease in the starlight. So yeah, this is just to show you an example of different transits depth you can observe when you are looking for different kind of planets. So the transit, as I said, the transit method is the most successful method. The Kepler spacecraft, which was launched by NASA, it was a transit survey, and it discovered thousands of planets. So the main goal of Kepler is to discover Earth-like planets. It was launched by NASA in 2009. It is not operational anymore, but this satellite has observed 150,000 stars over a period of 5 years, and it discovered thousands of planets. So this mission is not working anymore, but we do have an active mission, again launched by NASA. It is called TESS, the Transiting Exoplanet Survey Satellite. It was launched in 2018, and it is again doing the survey of the nearby solar neighborhood. And the primary mission objective of this TESS satellite was to do a survey of the bright star and to detect an Earth-like planet. So till now, it has detected more than 170 planets. It has already gave more than 500 planetary candidates, and it is expected that we will be able to discover more than 20,000 planets using this mission. Okay, the last method, the indirect method, which I'm going to talk about, is we call gravitational microlensing. So this method works on the gravitational bending of the light. So you can see here, this is a distance. So this blue dot is the Earth. Let's say the observer sitting here on the Earth, and this sorry, just wait for a second. And this star, the distant object, is the background star, and this is suppose that this star planet system is passing in front of it's passing in between this distant star and the Earth. Then it, because of the gravity, it bends the light which is coming from this distant star. So what you see, as the time passes, and when this star comes in front of the Earth and this system, you see increase in the light. And because of the presence of the small planetary body, it also magnify the light which is coming from the distant star. Just to show you again, so when the star with planet is coming passing in front of this between us, you see increase in brightness, and this planet also increase or magnify the light which is coming from this star. This is how this gravitational microlensing work. Only very few planets have been discovered using this technique. Yeah, so this technique is called gravitational microlensing technique. So yeah, I discussed about different kind of planets which we do see, different types of orbits, eccentricity, inclination. Some are orbiting very close to stars, but how many of them are known to be habitable? Do we have such information about their habitability? So, okay, before going into detail, the habitable zone is we always call or refer it as a Goldilocks zone. So it's a zone where a star, it's a zone around the star where the condition might be just right to support the existence of liquid water on the surface of the planet. As we know that the liquid water is a very crucial ingredient for life. So here, what I'm showing you is so in the bottom figure is our inner solar system. So Mercury, Venus, Earth, and Mars. And on the upper figure is a TRAPPIST-1 system. TRAPPIST is the name of the star. So compared to our Sun, this star is a very cool star, and it's also very small compared to Sun. But the interesting thing about this star is that it hosts 7 planets. Yeah, 7 planets. And out of the 7 planets, 3 planets E, F, G happen to be in the habitable zone. But if you just compare the orbit of these planets compared to inner system, inner solar system planets, then they are orbiting in a very close tight orbits. But since the star is very cool, the habitable zone is very near towards it's a bit near to the parent star. In contrast to the our solar system planet, habitable zone in our solar system planet. So these are some systems which people have or scientists have found that the planet around them could be in a habitable zone. There are much more examples. There are furthermore examples of such systems. So we know and think that we have a small Earth-like planets in habitable zone around these stars. But how can we tell or figure it out whether they are inhabited, whether they are habitable or not? These are the major questions we try to answer, because we know that there are 5,300 exoplanets, out of which few of them are an Earth-like planet. But do they host life on them? So how we can tell that they have life on their surface or not? So the one way to tell about the habitability is to study the atmosphere. So what you see here, this is star, this is a planet, and during the transit, we know that the planet blocks the light. But if a planet has a very thin atmosphere, you can see here, then the upper part of this upper part of this atmosphere of the planet is partially transparent to the starlight which is passing through it. So some of the starlight while traveling through this atmosphere is filtered. And when you observe this filter light through instruments, you do see various molecules in their spectrum. What kind of molecule you can see is depending upon the type of molecules present in their atmosphere. So missing, and depending upon the molecules, we can tell this planet has this atmosphere, also these molecules or that molecules. So again, give an analogy how this transmission spectroscopy works. So the one thing you should all know that every molecule and an atom have their favorite wavelength at which they like to absorb the radiation. For example, sodium, it happened to be so sodium absorbed like a crazy at particular wavelength. In particular yellow wavelength, sodium love to absorb yellow wavelength. So if you have a star and a planet is going in front of the star, and if planet has an atmosphere, and if you absorb, if you observe this system, this planet, let's say in a yellow light, which absorbs the sodium. So what you see, if there is sodium present in the atmosphere, you will see it at the planet appear bigger in size, because all the sodium which is passing through that atmosphere is absorbed by the planetary atmosphere. So the planet appears bigger. And how it they look like when this is example. So in this plot, you have on x-axis a wavelength, on y-axis the radius ratio, and you can, when you observe this planet star system as a function of wavelength, so all these data, the black data points are the real observation, and you can see here this planet appears bigger at this wavelength, and this wavelength corresponds to sodium. So this is how scientists and the researcher are trying to understand the composition of the atmosphere, what sort of atmosphere they are made up of, You can tell about the molecules like CO2, H2O, many things you can tell about the planetary atmosphere using this technique we call transmission spectroscopy technique. So this is about the atmosphere of the exoplanets. Now let's talk about exoplanet science in India. So it's not that the people from Western world, they are just doing the exoplanet science, but India has also made a significant contribution to the field of exoplanet detection and exploration. And the scientists from India have been involved in various ground-based observation to detect and characterize the exoplanets. So the physical research laboratory where I'm working is a leading institute in India, which initiated the study of exoplanet in India. So the PRL, Physical Research Laboratory, hosts 2 telescopes in Mount Abu, in Aravind mountain in Mount Abu, Rajasthan. So here in this image you see a small telescope, a 1.2 meter class telescope, and this is a newly built telescope. It's a 2.5 meter class telescope. This is one of the most advanced telescope in India, which our institute PRL is hosting. And PRL has indigenously developed a spectrograph, which we call PARAS spectrograph. PARAS stands for PRL Advanced Radial Velocity Abu Sky Search. So this spectrograph is trying to detect planet using the radial velocity method, not transit method. So this is the image of 1.2 meter class telescope, and this instrument works in a wavelength range of 3,800 to 6,900 angstrom. The resolution of this spectrograph is around 67,000, and the precision of this instrument is around 2 meters per second, which means that with that instrument you can detect giant planets, or the planet which is similar to a Jupiter or even bigger than a Jupiter. Also sub-Neptune kind of planet. So this instrument, which we call PARAS, is on 1.2 meter class telescope, and we have an advanced version of PARAS 1. We call PARAS 2. It has a resolution of 100,000. It works in a wavelength range of 380 nanometer to 720 nanometer in a single shot. And we should be very proud that this is the first highest resolution spectrograph in Asia, actually. So this is the first one in Asia at that resolution. And with this instrument, and along with 2.5 meter class telescope, I'm sure that we will be able to detect an Earth-like planet. So what about the discovery of planets discovered by India? So these are the recent discovery by the scientists from PRL, TOI 4603b and TOI 1789b. These are real, as I said, the PARAS 1 works on a radial velocity technique. So this is a radial velocity curve. It's a phase folded curve, so you might not be able to see the sinusoidal nature of this curve, but you see this radial velocity curve, and this is one of the densest exoplanet our scientists have published in the literature. It is orbiting very close to its parent star, 0.0 AU. The distance between the star and the planet is 0.08 AU, very, very close orbit. Until now, only 8 exoplanets have been discovered of that density. The other planet is TOI 17896b. This is one of the most massive and dense. So the TOI 4603 is the least dense exoplanet, and this one is the most massive dense exoplanet. And this planet lies at the boundary between the planet and brown dwarf. So yeah, these are the kind of discovery the Indian scientist has made in past 1 year or so. And the good thing about these discoveries is that all these two discoveries comes from a PhD student who's working in PRL, and it's a girl actually. She's a girl, so the girl is doing very good in exoplanet science. So yeah, we should be very proud on them. And yeah, there are lots of media coverage on those discoveries also by the ISRO and various media newspapers. And yeah, I'll stop here. Thank you.